Hi, these are edited versions of the lectures that I taught synchronously over Zoom. I hope you find them useful. All right, let's get started. This is lecture 17, and this is going to be about the Bootstrap, okay? So, in this third part of the class, we talk about standard errors so far. Talk about the heteroscedasticity consistent standard errors. We talk about hack standard errors. We talk about the cluster covariance estimator to get standard errors. And in a way, that's about it, especially when we cover the finite sample adjustments on how to compute standard errors. And so today, we're going to keep in the same spirit. And today and tomorrow, that's the case. And we're going to think about how to do inference. Okay, at the end of the day, we're concerned about how to estimate standard errors correctly because we want to have a t-statistic that was asymptotically normal so that we can construct a confidence set or do hypothesis testing. Today, we're gonna just try to see if we can get the distribution of the statistic that we are gonna care about without using asymptotic normality. We're gonna use one of these methods that are called or belong to the family of resampling methods, okay? So the critical value of whatever we do are not going to be like a constant like 1.96 as we had so far. It's just going to be random. For every sample that we're going to get a different critical value, okay? And there are many advantages of the things that we're going to do today. We're going to describe them. But one of them is in particular that we're going to be able to use these methods or when computing standard errors is particularly complicated, okay? Could be complicated because depend on too many parameters, depend on parameters that are hard to estimate. Sometimes they're not even, may not even be known, but that's not so common. The most common case is that perhaps you have an expression, but the expression is hard to estimate. And even in cases where we can use the approaches that we use in so far, there may be other reasons to consider something like the Bootstrap. We're going to talk about the concept of pivots, asymptotic pivots, and then we're going to describe the Bootstrap. I'm going to start describing the algorithm, how you implement the Bootstrap in practice, and then I'm going to do some basic theory for the case of the sample mean. We're not going to prove the validity of the Bootstrap in general, but hopefully the case for the sample mean will show you how to think about proving results for the Bootstrap. So when I prove the result for the sample mean, I'm thinking more about students that are thinking about taking the topic sequences later. And it's more about how to think about the problem and how to prove things in general. And there's going to be some discussion in particular about the concept called refinements. So let's see. The setting is going to be we're going to have data that I'm going to denote by X, and it's going to be a sample of size N, and it's going to be IID from some distribution P. And this distribution P is going to belong to a family ball P. The family ball P may be parametric, non-parametric, semi-parametric, etc. So we can, X could be a scalar when thinking about the mean or something like that. Or it could be regression context, or it could be any other context. We're interested in making inferences about a parameter that I want to denote by theta p, and theta p is going to belong to a set theta, which is going to be theta p for all p in ball p. Okay. Examples of theta p are the mean, the median, the regression coefficient in a regression, and so on. Notice the change of notation here, which is X in my case is just going to be the sample that we have, and so in the case of a regression, it is including Y and X, everything you observe, okay? So since I'm not going to talk about regression in particular today, I'm going to just call it X, but X is all the data you observe, okay? And theta p could be beta in the things that we've been doing so far. As I said, the coefficients in a regression could be coefficients in a parametric model if you're estimating something more parametric. If you're estimating a probit model, the coefficient in a probit model, whatever it is that you're doing, it's going to be there. But it could also be some object like this conditional expectation of Y given X. Go back when we did non-parametric regression and all that discussion, you would call theta p the expected value of Y given X at a little x or something like that. Today we're going to introduce a concept that I haven't used so far, And that's going to be the following, the object that is going to be necessary for describing the properties of a confidence set. So a confidence set for theta p is going to be a random set that I'm going to denote by C. It's just as a function of the data, such that the probability that C contains the parameter theta p is approximately 1 minus alpha. Of course, we want this to be 1 minus alpha exactly. Sometimes we won't be able to get that, but just get this idea that at least we want this to be approximately 1 minus alpha, at least for n sufficiently large. And the typical way of constructing these sets is based off the approximating the distribution of something that I'm going to call a root. And the root is going to be denoted by the letter R. As I wrote here, a root is any real value function depending on both the data and the parameter of interest theta p. So every time I bring out roots, people sometimes get confused. And I would say, think about the t statistic. Okay, suppose that we have square root n x bar n minus some mean mu divided by sigma hat n. This is a root. Okay, why? Because the root is not something that you can compute with your data, because it always depends on a known parameter that you don't know. Okay, and in this case, that object would be mu. Whereas a test statistic, is something that you can compute. So typically, is suppose that you're estimating that the mean is equal to 3, you would do this. So this is a test statistic where you replace the unknown parameter by a guess value, typically the value under the null hypothesis. Mu is equal to 0, you put 0. If mu is equal to 3, you put 3. So a test statistic is just a function of the data, whereas a root is a function of the data and the unknown parameter, which in our notation today is theta p. Okay, so what we need to proceed is to get or talk about the sampling distribution of this root. The idea is that if the distribution of the root weren't known, okay, then we can just solve this problem immediately, okay, because that's all you need at the end of the day to construct a confidence interval for or confidence set for theta p. So we're going to denote this. We're going to use this notation where J is going to denote sampling distributions, and in particular J and P is going to denote the sampling distribution of the root R. And the CDF of this distribution, we're going to denote by Gn little x p, which is the probability that Rn is less than or equal than little x. Okay, so we're going to be use this notation sometimes. We're going to say Rn has distribution J and P, and the CDF, okay, is Jn xp. This is what I want to be doing. So notice, as I wrote here, that the distribution of the sampling distribution of our root depend both on the sample size, okay, and the distribution of the data p. And part of the problem is going to be that we don't know the distribution of the data p, okay. But for now, suppose that we knew this sampling distribution, this CDF, then we may choose a constant c, okay, such that the probability that the root is less than or equal to c is roughly 1 minus alpha. And so then we can construct a confidence set by just collecting all the values of theta such that the root is less than or equal than this one title. And this is going to satisfy the property that we described before. This is, of course, not the only way. Once you know the distribution, instead of choosing one constant c, you can choose two values, c1 and c2, and such that this inequality over here happens, where probability of R being in between c1 and c2 is 1 minus alpha. And in that case, you will just construct a confidence set by collecting all the values of theta like this, And then you lead to notions of confidence sets that are like symmetric, that are equitail, and so on. Most often here in what we have done in this class, we have used this approach where we just have one critical value. And for example, the root is the absolute value of x bar minus mu, or beta hat minus beta divided by something. But hopefully the idea is clear that if we know this distribution, if we knew this distribution, then, just get the quantile that you need, and then you're good to go. You have a confidence set with the properties that you want. So we're going to talk about 3 cases about how much we may know about this distribution, sampling distribution. So I wrote, in some rare instances, JNXP does not depend on P, okay? So even though you write JNXP, in reality, this distribution doesn't actually depend on P. And when this happens, you say that the root is pivotal, or is called a pivot. And an example of this is the following. There are not a gazillion of them. There are many, but not. It's definitely not the most popular case. But if theta p, for example, is the mean of p, and then bold p, which is the family of distributions that you want to consider, is just a set of distributions with mean theta and variance 1, or known variance, but in this case it's 1. Then the root, square root n x bar minus theta p is a pivot because this is exactly normal 0, 1. So this is the case where you have random variables for a distribution you don't know because you don't know the mean. But the root, which is square root n sample average minus the true mean, well, that doesn't depend on p. It's always normal 0, 1. So how can you do inference? Well, you can get here, in this case, a finite sample confidence set, okay, by collecting, defining C as in the previous slide, and then you're good to go. Because in this case, you know the distribution of the root because it's pivotal. So as I said, pivots are useful. And, if you go back to probably your intro stats class that you took at some point in your life, you may recall that, a lot of really intro stats books will just start covering inference about the mean of a random variable by dividing in cases whether the variance is known in the normal case, of the variance is unknown. And the reason of that is like when the variance is known, as in this example, you actually have a pivot, and it's the simplest case to do inference on the mean. But okay, as I said, this doesn't happen typically. So I wrote, sometimes a root may not be pivotal in the sense that we just described, but it may be asymptotically pivotal, or you can say that it's an asymptotic pivot. What is an asymptotic pivot? Is when j and xp converges in distribution to a limit jxp. Notice that here j is not indexed by n, so this is a limiting object, and the limiting object does not depend on p, okay? An example, the same one that we had before, but a lot more general. Here, theta p is the mean of p, and bold p is the set of all distributions with finite non-zero variance. So this is the set of distributions where we can apply a central limit theorem. And so in this case, the root, that is square root n x bar n minus theta p divided by an estimator of the standard error, is asymptotically pivotal because we know by the CLT that it converges to standard normal. So in this case, the limiting distribution doesn't depend on p. It's just standard normal. Typically we write this as converges in distribution to a normal 0, 1, and the normal 0, 1 here does not depend on p. That is, you don't know. You know where you started. You know that you may have had a distribution with whatever mean, whatever variance, but this root is such that the limiting distribution doesn't really depend on where you started. Just go to a normal 0, 1. So using this, we just construct find C as in 2 slides ago, or C1, C2, depending on how you define it, and then you can construct a confidence set that is going to satisfy this property that at least the limit as n goes to infinity of the probability that the confidence set includes the parameter is equal to 1 minus alpha. And this is going to hold for any p in the family. So that's pivots, asymptotic pivots. In a lot of the cases, you don't have either of them. So typically the root will neither be a pivot or an asymptotic pivot. And the distribution jnxp and the limiting distribution jxp will typically depend on p. An example here is just consider the same one that we did in the previous slide. but now do not standardize by sigma hat. So you just have Rn is square root n x bar minus theta p. So in this case, this will converge to a distribution. If you write it in the way that we used before, this converging distribution to a normal 0 variance sigma square p, let me call it. And so this distribution in the limit does depend on p. The finite sample distribution of the root depends on p. The limiting distribution also depends on p through sigma square p. And so you can write it like this. jxp is just the standard normal CDF of x divided by sigma p. So the fact that you don't have an asymptotic pivot doesn't mean that you cannot use this result. So what you typically do is that, as I wrote here, we can approximate this limit with the CDF of standard normal, and you replace the object that you don't know, sigma p in this case, by sigma hat n. And this is going to lead to confidence sets that are asymptotically valid in the sense that we described before. And this is called, as I wrote here in the title, an asymptotic approximation. Just take it into infinity. You get to an object that depends on parameters that you don't know. You estimate those parameters, and then you just use a quantile from that thing. This approach depends here on what I wrote very heavily on the limiting distribution jxp being both known, okay, we know how it looks like, and it is tractable, okay, something that we can know how to manipulate. Because sometimes, even if it is known, the limiting distribution may be very difficult to work with. And this happens in a lot of models and frameworks that lead to things that are more complicated. As I wrote here, for example, it could be the supremum of some complicated stochastic process with some nuisance parameters and so on. And even if it is known and manageable, the method may be poor in finite samples because it essentially relies on a double approximation. You first approximated the distribution that you care about, the finite sample distribution jnxp, with the limiting version jxp. But then you approximated jxp with some, way of estimating the limiting parameters in the distribution. As I wrote here, we approximated the sampling distribution with this object, but we didn't use that object because we didn't know sigma p. So we ended up using this object that had sigma hat instead of sigma p. So there's a double approximation. And the double approximation, whenever you have multiple approximations going on, there's a higher chance that at some point some of those may be poor, and then the performance of the methods is affected in finite samples. So when it comes to the things that we've been using so far, is summarized in these three cases. You have either a pivot, which we essentially never had in this class, except when we talk about the variance-Fisher problem. Then you may have an asymptotic pivot where we have a lot, okay, because I made sure to use roots that were asymptotic pivots, okay. But we also had cases in which limiting distributions depended on objects that were like this. For example, when we did non-parametric regressions and we talk about the distribution of the estimators, right? That's a root. And so these three cases are cases that we cover in the class. Today, we're going to consider a fourth method that is called Bootstrap. And as I wrote, the Bootstrap is a fourth, more general approach to approximating, okay, the sampling distribution of the root. The goal is the same. The approach is going to be different. The idea is very simple. Replace the unknown p, which is the problem of this finite sample distribution, with an estimate of p that we're going to call p hat. And given p hat, it is possible to compute jn xp hat. And what's important here is that this can be done either analytically, which often doesn't happen, or by simulation, okay, to any degree of accuracy. And this is what is typically done in practice. So when you're dealing with the Bootstrap and you want to estimate it in an empirical, say, situation, you're going to be using simulation 99.9% of the time. And then when you're doing proofs about the Bootstrap, you're going to be working with the analytical expression, okay? So we're gonna talk about it. So what's an estimate of p hat? As I wrote here, the estimate there are more than two, but there are two that are certainly the leading cases. The first one is when the data is IID, you can use the empirical distribution of the data. The empirical distribution is the distribution that puts mass 1 over n on each observation that you have in your sample. Okay, you have a sample of size n, and so each value that you get to observe has probability 1 over n. That's the empirical distribution of the data. However, if you're working with a parametric model, let's say that you're using maximum likelihood, or say you're using a probit, a logit, or something like that, then you can do parametric bootstrap. In that case, P is just P of some finite dimensional parameter here, psi, whatever the parametric model is. And so what you can do is estimate psi with some estimator, consistent estimator of psi hat n. And so now you know the distribution P hat n. Okay, suppose you assume the data comes from, I don't know, a normal with mean mu and variance sigma, and then you can estimate mu and sigma, and then you can just simulate values from a normal with mean x bar and variance this sample variance. And that would be a parametric approach to get an estimator of the distribution P. Regardless of whether you go from for 1 or 2, the hope is that whenever the distribution P hat is close to P, meaning whenever you have a good estimator of the distribution of the data, that the sampling distribution at P hat is close to the sampling distribution at P. Okay? So if P hat is really similar to P, the hope, as I wrote here, and I wrote hope, is that this distribution is similar to this one, which is at the end of the day what we want. And this, if you just view this object as a function of P, it requires this distribution to be continuous in a certain sense, okay? I'm not going to get into the technicalities of what this continuity means because P is an infinite dimensional object, it's a distribution. So we're asking for a continuity as a function of an infinite dimensional object, but at the end of the day, it's not that different than the usual notion of continuity, which is captured in this sentence over here. That is, if P hat is close to P, you want this function of P to be the function of P hat to be close to the same function at P. So often, as I wrote, this turned out to be true, and that's why the Bootstrap is very popular and widely used. But, one thing that it is important is not true in general. And by that I mean there are already a lot of known cases that are popular, sometimes in economics, I said in particular in IO, where we know that the Bootstrap fails, okay? And so it's true that sometimes people just use the Bootstrap in situations where we don't know if it actually works or not. That is more popular than you may know, but it should always be questioned whether you think that more or less there are hopes that the Bootstrap to work or not. And then, as I said, this is not something that I want to cover in this class. In 481, we talk about regular and irregular cases, and we just get typically, hopefully, a better sense on when the Bootstrap would be expected to work or not. But as I said, it works quite generally in a lot of important cases. For example, regressions that we have talked about. Most often, that's a case where the Bootstrap tends to work under mild conditions. A rule of thumb is that whenever the limiting distribution is weird, or whenever we have maximum, minimums, and things like that going on in the expressions of these distributions, you would expect the Bootstrap to fail. If I can give a simple rule of thumb, that would be it. So those are the 4 ways of approximating, this sampling distribution that are relevant for today. And now I'm gonna get moving to talk more in detail about the Bootstrap. Before I do so, let me know if you have questions. All right, so let's get going. I'm gonna discuss the case of the sample mean just for concreteness. But as I said, the Bootstrap can be applied to pretty much any situation. We will consider the case where P is the distribution on the real line, so it's just a scalar, R, and theta P is the mean of P. So the root that we're going to consider is square root n x bar minus theta P, which is the one that I said before. And we're going to start thinking about P hat being the empirical distribution of the data. And as I said, the empirical distribution of the data is just the one that puts mass 1 over n at each observation that you get to observe. The question is, under what conditions is the Bootstrap distribution, which is JNXP hat, close to the sampling distribution of the estimator. And what we're going to do is to present a theorem that is going to tell us under what conditions the Bootstrap works for the case of the sample mean, or the mean of a scalar random variable. One thing that makes the arguments complicated is that the sequence of distributions p hat n. Now we're going to have observations that come from this distribution p hat n, but this distribution is random, okay? Because it assigns mass on random points. So what we're going to do, and one way, this is not the only way, but it's the way that I like to think about the problem, is to split the arguments into. First, we're going to prove things for a non-random sequence that I'm going to call Pn. We're going to just artificially define a non-random sequence of distributions Pn, and we're going to prove that if we could sample from this artificial Pn, then the Bootstrap using Pn would work, okay? And Pn would not be random. The proof really simplifies. And then the second part of the argument is going to be that the empirical distribution p hat n is essentially satisfying all the requirements that we impose on Pn almost surely. And that's it. So you split the proof in two. There are other ways to make formal statements about the Bootstrap, which involves conditioning on the data, because then when you condition on the data, this empirical distribution becomes non-random, conditional on the data, but then you have to start doing all arguments that are conditional. So I'm not saying that one way is better than the other. There's a way that I decided to use in this class. However, before we present these results where we're going to start using this non-random sequence and so on, I want to discuss how to implement the Bootstrap, okay, in practice for this particular case, so that if you fall asleep later, at least you know just how to do it, and then we are done with the cookbook part of today's lecture. So, implementation of the Bootstrap. I said most often the Bootstrap approximation cannot be calculated exactly. It's not an analytical expression. So we have to simulate this. And I wrote we can approximate the distribution to an arbitrary degree of accuracy by taking samples from this empirical distribution p hat n. We're going to consider two cases for the case of the mean. The first one is that when bol p, I call here bol p np, is distributions with finite second moments. So NP stands for non-parametric Bootstrap, okay? And the second one is where bol p is parametric. For example, P is the families of distributions that are exponential with parameter 1 over theta. Just as an illustration to contrasting cases, one where we have a parametric model and one where we have a non-parametric model, or semi-parametric if you want, as we're assuming that there are second moments and so on. The implementation of the Bootstrap requires 4 steps, and I'm going to go through these 4 steps. And if you understand the 4 steps, as I said, you can apply the Bootstrap to any situation. First, I'm going to say conditional on the data. It's a sample of size n. We're going to draw B samples of size n from the distribution p hat, okay? And we're going to know the jth sample by x1 star j, xn star j. And how many samples like this we have? Capital B. In the non-parametric case, bol p is this guy, the non-parametric. So p hat is typically the empirical distribution of the data, the one that we said before. And I wrote here, this involves resampling the original observations with replacement. Each observation has probability 1 over n. In the parametric case, where bol p is this family over here, then, you can estimate theta, say by maximum likelihood. And so in this case, p hat is just going to be exponential distribution with parameter theta hat n, okay? Or theta hat n in this case just going to be the sample mean. So you can ask your computer to give you a sample of size b, or size n, from this distribution. How many samples are you going to get? B, as I wrote here. Notice that your original sample, the size of your original sample, which is n, and the size of your Bootstrap samples is also n. Those two coincide. That is important for the Bootstrap. And actually that is important for the properties of the Bootstrap. And also I wrote here in the case of the empirical distribution that you sample with replacement. That also is important for the Bootstrap, as we're going to be contrasting later on with things like step sampling, where there's not going to be a replacement. So I wrote here, note, step 1, how you take your samples determines the type of Bootstrap that you use. And I wrote here parametric, non-parametric, which are the two that I described, but the others that I'm not going to describe, for example, wild Bootstrap, cluster Bootstrap, and so on. But the first step where you determine the type of Bootstrap that you use is here. How you get your samples determines the type of Bootstrap. If tomorrow you learn about the wild Bootstrap, you're going to see that the wild Bootstrap is going to essentially change this first step. Is going to keep steps 2, 3, 4, and change. Okay. Step 2, for each Bootstrap sample J, you're going to compute the root that you have again. Okay. And remember, data in the Bootstrap world comes from the distribution p hat. And so in the Bootstrap world, on these samples you're taking, the true theta is theta p hat, which is theta hat. For example, if we're talking about the mean, as in this case, well, this is going to be the sample mean. So your root is going to be the same expression where you just plug in the Bootstrap samples. It's going to be centered by theta hat n. So in the case of the root that we're discussing today, rj star n is just going to be square root n, the sample mean of the Bootstrap observations minus the sample mean of the original sample, that is theta hat n, which is x bar n in this case. So that's the second case. So how many times are you computing this object? B times, okay? Because you have B samples. For each of these, you just go and compute this rj star n. Once you have all these B values for this root, you're going to compute the empirical CDF of this, and I'm going to call it lnx, which is just 1 over b, the sum over j, 1 through b, of the indicator that these roots are less than or equal than some value x. And by the Ivan-Canay theorem, as I wrote here, this approximates the distribution of the Bootstrap distribution, jx b hat n, very well uniformly over any point in the support as b goes to infinity. And so Bootstrap, we're using an approximation here, but we have control over the accuracy of this approximation, okay? I wrote here the Ivan-Canay theorem implies that we can achieve an arbitrary degree of accuracy by choosing b sufficiently big. In practice, I said researchers just use values like 1,000, okay, or above, as long as you have computational power. And since computational power for this type of things tend to not get in the way, it's common that people use large values. And what happens is that when you just get to a good approximation, if you use 1,000 and 2,000, your numbers don't change much because, you just sort of like got to the end. And if your numbers are changing, well, you can just use a larger value of b. So as long as, you have computer power, you can use a larger value of b. So the idea is to use this empirical CDF to get a quantile. So how do you get a quantile? As I wrote here in step 4, compute the desired function of this CDF, for example, a quantile. And so this is just the definition of a quantile, which I'm denoting by ln inverse 1 minus alpha. In practice, okay, if you just do this in a computer, step 3 can be skipped, in particular because most often we're looking for quantiles. So as I wrote here in practice, usually skip step 3, okay, and compute step 4 directly using some quantile function. Generically, whatever software you're using, you're going to say, what is the quantile that you want? It's just the 1 minus alpha quantile of your list of roots that you computed for each Bootstrap sample. So in reality, you're just going to have 3 steps most often. You're going to get your draws in step 1. In step 2, you're going to compute the roots for each of these samples. There are B of them. And in step 3, you're just going to compute the 1 minus alpha quantile of this list. Okay? But conceptually, it is better to think about the Bootstrap in these 4 steps. And also, like if you need something that is not the quantile, then sometimes you will need to compute the empirical CDF. So in step 1, it matters the family of distributions. As I said, it matters how you get your draws. Could be parameters. That's here, parametric. Parametric versus non-parametric. In step 2, it matters what the parameter of interest is and what the root is. If you're using different roots, that's going to affect your step 2. And step 3, maybe skip if step 4 can be calculated directly as above. It could be a quantile. If you care about something else, you can just apply that function directly. Okay. So, but this is how you estimate or implement the Bootstrap in practice. And before actually I move to the formal results, I'm going to show you a picture with illustrations with marbles, because I think it sometimes helps clarify things. This should be B. This is B. And so suppose that this is, in a way, this list at the top here is the population. Okay, so these marbles of different colors, and you get a sample of size n. And the sample of size n is this list of marbles that you got. I want you to pay particular attention to some colors. Okay, so notice, for example, that there are 2 greens. Okay, and all right, let's see if I can see the colors well here. There are actually 2 blacks. This is a black one. There's a black one. So green and black, they're 2 of each, right? And so when you look at the Bootstrap samples, you have, how many balls are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 20. And so you take samples of size 20, where each of these balls get probability 1/20, and they're like sample with replacement. So what you see here is that it is very common for the Bootstrap to have situations where there are values that are repeated, right? So see here in the original sample, there were 2 green balls, but in one of the Bootstrap samples, the last one here, there are 5 green balls, okay? And so, and actually, there's only 1 black ball. So not all values are going to show up. Sometimes there are some observations don't show up in your Bootstrap sample. Sometimes there are observations that appear multiple times in your Bootstrap sample, and that's totally fine. That's what makes the Bootstrap works. Okay. So of course you can see this with numbers. You can actually try to plot numbers yourself. But I thought the marbles were an easy way to illustrate that visually. All right, any questions about this before we proceed to do some formal statements about the Bootstrap? So let's move to the formal statement about the validity of the Bootstrap for the sample mean. The theorem reads like this. And as I said, I wrote here intermediate step non-random sequence. I want to just prove a theorem in a vacuum about some distribution that we don't know. It says the following. Let theta p be the mean of p, and let bold p denote the set of all distributions on the real line with finite non-zero variance. Okay? Again, these are distributions where we can apply central limit theorems. Consider the root, Rn is square root n x bar minus theta p. Let Pn be a sequence of non-random sequence of distributions such that 3 conditions hold. Okay, and this is important. The first one, Pn conversion distribution to P. The second one is that theta Pn converges to theta P. And the last one is that sigma square Pn converges to sigma square P. So I'm just telling you, suppose that we have a sequence of distributions Pn. Okay, what is this? We don't know. I'm just telling you that it's a theoretical object. And this object satisfies 3 properties, these 3 that I'm listing here. Then if this happens, then we have 2 results. The first one says JNXPN conversion distribution to JNXP. And the second one is that the 1 minus alpha quantile, okay, of this distribution that has Pn converges to the 1 minus alpha quantile of the limiting object. There are a few things that I want to emphasize. The first one, the former result is asymptotic, okay? That is, it's a statement about approximating the limiting distribution, not the distribution with n. going back to the question that we had before. Okay. So when people think about, oh, Bootstrap finite sample is like, is better in finite samples and things like that, that is not a statement that follows from this type of theorems. It's just gonna be there's gonna be a sense in which the Bootstrap is gonna perform better in finite samples, and we're gonna discuss that after we present the formal result. But when you think about the theorems are asymptotic, and the Bootstrap is an asymptotic tool whose validity depends on taking n to infinity. Okay, and that's what we're gonna do. We're gonna take n to infinity in our proof. Okay, so when people say the Bootstrap is valid, it means that it approximates the asymptotic distribution of the root. And so what we're gonna do is we're gonna prove this part. The second part I'm gonna write as a lemma, and the proof is gonna be in the lecture notes. Okay, it's not difficult, but I don't want to waste time with that. And then we're gonna prove this theorem. This theorem is not a proof that the Bootstrap works because the Bootstrap doesn't use Pn. We're gonna need a second part where we claim that using p hat n is essentially similar to using Pn. And so what we'll need to check at some point is whether these three conditions hold for p hat n or not later. So I'm going to say here later, the question is going to be, does p hat n satisfy these conditions? Almost surely, or not? The answer is, of course, going to be yes, and that's how we're going to prove that the Bootstrap works. Are we good? All right, so we're going to prove one. So I wrote here for each n, we're going to denote this double index notation, which is xin, which each observation here is going to have distribution pn. So we have what we call a triangular array. We want to show that the square root n x bar and n minus theta pn converges in distribution to a normal with mean 0 and variance sigma squared p. To do this, we're going to let define zin as xin minus theta pn divided by sigma pn. And we're going to apply the Lindbergh-Feller CLT. So what we need to check is the uniform integrability condition in that that you need for that theorem. So it's going to be the limit as n goes to infinity of the expected value of zin square times the indicator that the absolute value of zin is greater than epsilon times square root n. This limit 0 for any epsilon positive. So I'm going to say by conditions 1, 2, and 3, we have that zin converges in distribution to what I'm going to call z, which is going to be x minus theta p divided by sigma p, with x having distribution p. Notice that Zn has three objects: the x, the theta, and the sigma. Condition 2 says that sigma Pn converges to sigma P. Condition 3 says that, theta Pn converges to theta P. Condition 3 says that sigma Pn converges to sigma P. And condition 1 says that the distribution Pn converges to P, the Pn converges in distribution to P. So xn converges in distribution to x, where x has distribution P. So this is the object that we're going to deal with in the limit. And so the claim that I'm going to write here, claim, is that for any lambda in the real line for which the distribution of the absolute value of z is continuous, we have the expected value of zin square times the indicator that the absolute value of zin is greater than lambda, converges to the same expectation where zn is replaced by z. Note, I'm going to say here, this doesn't follow directly from star. Where star is this? So we want to prove this thing here at the bottom. Okay. Oops. But this red star doesn't follow from the blue star because convergence distribution doesn't imply convergence of moments. So in order to prove this result, we need to use two intermediate results or two lemmas, and that's going to be the next slide. But for now, the sort of like wrap up where we are is we want to show this, right? And to do this, we use this random variable z, and essentially what we need to check is this integrability condition that we need to invoke the Lindbergh-Feller CLT. And so we're going to do this. This is what we want to prove. But first, we want to be able to show this, that for any lambda for which this distribution of the absolute value of z is continuous, that this two moments, that this moment in a way approximates this moment. And we're going to do this with two results. So the first one I wrote here says that suppose that yn and y are real value random variables and that yn converges in distribution to y. Okay. Then if yn are uniformly bounded, then you have convergence of the means as well. Okay. So we're going to go from convergence distribution to convergence of moments. And the first part of this intermediate results tells us that we can do that as long as we can claim that the sequence of random variables in the statement, the yns here, are uniformly bounded. The second part is suppose that you have the yn convergence distribution to y, and we're going to let G be any measurable map from the real line to the real line. If C are the set of points in the real line for which G is continuous, and if this set of points have probability 1 under the distribution of y, then G of yn converges to G of y. This is the continuous mapping theorem. Okay, I'm restating here the continuous mapping theorem to sort of like refresh your memory that the continuous mapping theorem actually, allows for the function g to be discontinuous in some points. Okay, just that you need the set of points of discontinuities to have probability 0 under the limiting case, which is something that is going to happen here. We're going to may have 1 point or a set of points where this function is discontinuous, but those set of points are going to be going to have 0 probability. So two results then, going from convergence distributions to convergence of moments. And the second part is the continuous mapping theorem, where we're just being explicit about the set of discontinuity points. Okay, so let's do this. So now we're gonna let G of the absolute value of x be defined. I'm going to define a function. It's going to be the absolute value of x squared times the indicator that the absolute value of x is less than or equal to lambda. And then we're going to apply this to two random variables. One is going to be zin. So this is just going to be zin squared times the indicator that zin is less than or equal to lambda. And then g of z, which is the limiting version, z squared times absolute value of z less than or equal to lambda. Okay, and I'm going to say note g of zin takes values in 0 and lambda square. So it is uniformly bounded. All right. By 2, we have that g of the absolute value of z and whatever conversion distribution to g of the absolute value of z. Okay, because the probability that the absolute value of z is equal to lambda, which would be a problem because that's the point of discontinuity, is 0. Okay, we know that because in this slide I wrote for any lambda for which the distribution of z is continuous. Okay, so we have that. And so next, I'm going to write, the expected value of zin squared times the indicator zin is greater than lambda. Well, this is going to be, let me just write expected value of zin squared minus, expected value of g zin. This is expected value of z squared minus the same expectation. This converges to expected value of c squared minus expected value of g of z, which is expected value of c squared times the indicator that the absolute value of c is greater than lambda. I'm going to say this bar over here because expected value of zin squared is 1, which is also the expected value of c squared. So in this second part, we show the claim that we had in the previous slide, which is for any lambda, which is continuity point of the distribution of the absolute value of z, then we have that the expectation of zn squared times the indicator that the absolute value of z is greater than lambda. You can write that as the expected value of zn squared minus the expectation where the indicator is less than or equal to lambda, which is our definition of g. And then in the first step, we'll replace the expected value of zn squared by the expected value of z squared because both are 1. And in the last step, we take n to infinity, and the expected value of the g function converges because g is uniformly bounded, and we can apply this first thing over here, right? So I should say, which I didn't say, that this follows by 1. 1 is this. And so we have this result, okay, where we have this convergence of this object. And so all we need to do now is to use this result to prove that we satisfied the Lindbergh-Feller condition, which is the next slide. So the claim then is that we have everything we need to show this integrability condition in the statement of the Lindbergh-Feller CLT. And we're going to say for any lambda positive and epsilon positive and n sufficiently large, notice that we have the expected value of zin squared times the indicator that zin is greater than epsilon divided by square root n is less than or equal than the expected value of zin squared times the indicator that zin is greater than lambda. Whoops. Oh, come on. Because epsilon square root n is greater than lambda for n sufficiently large. This are reversed. This should be in. I'm gonna correct that. So now what I do is this. I want to take limits as n goes to infinity on both sides. I want to take limits as lambda goes to infinity on both sides. So it's just going to look like this. Lambda going to infinity. Limit as n goes to infinity of this thing. I'm doing 2 steps in one here because to save some space. But you could take the limit as n goes to infinity first, and then notice that the left-hand side doesn't depend on lambda at all. So now this is equal to the limit as lambda goes to infinity of the expected value of z squared times the indicator that the absolute value of z is greater than lambda by the result that we just proved. We just proved that this object here converges to this object. And so this over here is equal to 0 because expected value of z squared is finite. Then it followed by square root n, z bar, and n convergent distribution to a normal 0, 1. And this is what we wanted to prove. That's the claim of the first part of this theorem. The second part was a statement about the quantiles. And as I said, I'm not going to prove those. The statement about the quantiles follows immediately from a lemma. The lemma is this one. It says if you have Fn and F be non-random distribution functions on R, and Fn convergent distribution to F, if F is continuous and strictly increasing at the quantile, then the quantile of the quantile of Fn converges to the quantile of F. Okay, and as I said, the proof is in the lecture notes. I'm not going to do it, but the second part follows immediately from this lemma. Once you just apply to Fn being equal to Jnx, and f being equal to this. This should be, actually, there's a mistake here. It should be Pn. And that's that. That's the proof of the result for the non-random sequence. Now we may just gonna state where there's nothing to prove, as you're gonna see. We're gonna state the validity of the bootstrap for this case. The theorem says, let theta p be the mean of p, and bold P denote the set of all distributions on the real line with finite non-zero variances. Then consider the root, square root n x bar minus theta p. Then j n x p hat, conversion distribution to j n x p. And the quantile of the distribution with p hat converges to the quantile of the distribution with p. Now, this is a statement about the bootstrap, because here we're talking about the bootstrap distribution. So how do you prove this? It follows immediately from the lemma that we just, the theorem that we just proved, because the empirical distribution converges the distribution to p almost surely. This follows by Ivan-Canay theorem again. The sample mean converges to the mean almost surely by strong law of large numbers. The sample variance converges to the variance almost surely, again, by an application of the strong law of large numbers. Okay, so these two parts follows from strong law of large numbers, and this part over here, Ivan-Canay. And that's it. We have that the previous theorem holds, where the empirical distribution satisfy the requirements that we impose on this distribution Pn almost surely. And this is the formal result about the validity of the bootstrap for the sample mean. Remarks. Similar results hold for studentized root. So if you see here, we just derive this result where there's no sigma hat in the denominator. You can put sigma hat in the denominator, you prove the same thing, but the proof is more involved, okay? Using this root leads to the so-called bootstrap T, if you just studentize, okay? As the root is just the T statistic. So sometimes people say bootstrap, bootstrap T, and so on. I said a key step in the proof of this result is to show that sigma hat n converges in probability to sigma p under an appropriate sequence of distributions. This, as easy as it looks, ends up being challenging, or at least more involved. So I typically always do that in 481. The advantage of working with a studentized root is that the limiting distribution of this root is pivotal, okay? And there are reasons for being interested in having asymptotic distributions that are asymptotically pivotal. I want to discuss those reasons in a minute, which affects the properties of the bootstrap, as I wrote over here. By Slutsky's theorem, if you just do the confidence set like this, meaning you collect all the theta such that the root is less than the bootstrap critical value. This is something that I want to call here is a bootstrap critical value. So I said by Slutsky's theorem, if you just compute this type of confidence set, which is also called symmetric confidence sets, or this one's over here where you took the alpha over 2 quantile and the 1 minus alpha over 2 quantile on each end, which are called equitail, both cover theta with probability 1 minus alpha asymptotically. Okay, notice I want to stress again when we say the bootstrap works, what's going on is a limiting statement. There's an arrow there. We're not saying that the probability is equal to 1 minus alpha for every single n. It's an asymptotic result. Are there any questions about this before I talk the refinements? There's a reason why people often will say that the bootstrap may offer benefits, and it is true, but because under some conditions the bootstrap may work better than an asymptotic approximation. So the question is, what does it mean better? And that is called asymptotic refinements. Okay, the question here I wrote, is the bootstrap better than an asymptotically normal approximation in this case? For example, when we're talking about the mean, the answer is yes. Under certain conditions, ensuring the existence of the so-called Edgeworth expansion of this distribution, which of course I'm not gonna discuss here, it follows that one-sided confidence sets based off the asymptotic approximation, okay, when we do say we just use the quantile for normal and so on, are such that the coverage that we actually get, or let's say it again, the difference between the coverage that we get from our method and 1 minus alpha, which is what we want to get. Suppose that you take 5% as alpha, and then you want a 95% confidence interval. The actual coverage that we get in any given finite sample deviates from 95% at a rate 1 over square root n. So this is called the error in coverage probability, and it's just the error that you make, okay, from using an approximation. You want to get 95%. You are not going to get most often 95%, but you can say that the error is now going to be larger than this, and in particular, it's also say the error is going to disappear as n goes to infinity. How fast? Well, 1 over square root n. And this is where we get all the time with essentially everything we discussed in this class up until today. So I said one-sided confidence sets based off on the Bootstrap, okay? And this root that is non-studentized, okay? The one that is just square root n x bar minus theta p, the one that we actually show in the theorem, also satisfy 1. Although there's some evidence I wrote here that suggests that it does better. This is evidence that is based mostly on simulations and other stuff. Theoretically, it's also has an error that is 1 over square root n. Okay. Now, if instead of using this root, which is the one that we use in the proof of the theorem, we use a studentized root, the one that has an asymptotically pivotal distribution, then you can show that the error and rejection probability of the Bootstrap is actually of order 1 over n. So what this means is that the Bootstrap here also makes an error, is also an asymptotic result. But the difference between what you want, which is 1 minus alpha, and what the Bootstrap gives you, which is this coverage over here, tend to be closer to each other than what an asymptotic approximation gives you. And this is called a refinement, okay? It's not about the Bootstrap being valid in finite samples. It's about the Bootstrap having an error that goes to 0 at a faster rate than a normal, usual approximation, or what we call an asymptotic approximation. So I wrote here refinement. The coverage error of the Bootstrap t interval is of the order 1 over n, and it is smaller than the order provided by the normal approximation or the Bootstrap based on non-studentized roots. So there are two things that are important in this slide. One, you need some technical conditions for the Bootstrap to give you this extra benefit. Okay, those are the conditions that I call here, the ones that gives you the validity of an edgework expansion. But two, it is important that you are using a root that is asymptotically pivotal. Okay, the Bootstrap gives you, or has the opportunity to give you, the so-called refinement when you use roots that are asymptotically pivotal. If the root is not asymptotically pivotal, like the one over here, then you pretty much know that the Bootstrap is not going to give you a refinement. People may steal the Bootstrap anyway, even though you can say at that point, well, there are no benefits, because, as I said here, some evidence says that it tends to work better, so people just, sometimes just use it. But if you're using with an asymptotically pivotal test statistic, I would say even if there's no proof for the setting that you are considering, there's a high chance, in a way, that the Bootstrap is going to give you a refinement. And if the Bootstrap gives you a refinement, it gives you this confidence that even though we're using asymptotics, even though asymptotics are approximations and don't give us exactly what we want, the error that you're making with the Bootstrap is actually smaller. And this is part of the reason why people sometimes are really excited about the Bootstrap. So, asymptotic refinements. The heuristic reason why the Bootstrap based on the studentized root outperforms the Bootstrap based on the non-studentized root is as follows. In the non-studentized case, the Bootstrap is estimating a distribution that has mean 0 and a known variance sigma squared p. The main contribution to the estimator error is the implicit estimation of sigma squared p by sigma squared p hat. In the studentized case, the studentized root has a distribution that is nearly independent of p, since it's an asymptotic pivot. The Bootstrap may also provide a refinement in two-sided tests. I just gave the example of the one-sided case, but if you're doing the absolute value of the t-statistic and you do a two-sided test, then in that case, the difference is that the Bootstrap may give you an error that is of the order 1 over n squared versus the asymptotic approximation error, which is of the order 1 over n, okay? You see that doing two-sided tests has a smaller error than doing one-sided. And so I know that by construction, such intervals are symmetric about the theta hat. And so this is what we tend to do because we use the absolute values of t-like statistics. And so in this case, again, if we're using the right test statistic and if we have, we're in a situation where those technical conditions apply, then there's hope for the Bootstrap to work better. The final comment is that the Bootstrap may fail. It may work poorly in finite samples when this distribution is not continuous in P. And being a technical condition, it makes it harder if I give you a sophisticated setting and I ask you, do you think that the Bootstrap is going to work? It's sort of like really hard as a practitioner to get a sense of when the Bootstrap may work and when the Bootstrap may fail. But what I wrote here is that this happens in some settings relevant to economics. And as I said before, IO in particular, auction models, entry games, models where there's missing data, and so on are cases where we know the Bootstrap fails, at least in the form that I'm describing it here. And why? Because as I said, the cases in which you have limited distributions that depend on some, say, nuisance parameters, maximum, minimum, supremums floating around, and so on, are cases where you know that the Bootstrap fails. And probably the most famous and simple case, which is not related to economics, but where the Bootstrap fails, is if you just have observations X that are uniformly valid with between 0 and theta, and you want to make confidence intervals for theta. You know that the uniform, if you do maximum likelihood, the estimator theta hat n is just going to be the maximum of all these observations. Okay, and so if you just Bootstrap, and even if you do, if you just Bootstrap from the empirical distribution here, there's going to be a problem because this estimator by construction is always going to be less than or equal to the true theta. And so that creates a problem, as opposed to other settings where your estimator may be above or below here. So I would say if you are asking for the simplest example where the Bootstrap fail, certainly not the most interesting, would be the case of the uniform. But as I said, related to economics, auction models, where you just, the winner is depending on what framework you're using, but suppose that the winner takes the object, you have the maximum valuation, okay, as the winning bid. And so you start having, again, maximums and minimums floating around. That is a red flag. Entry games are also a situation in which you have multiple equilibria, and then situations where there's multiple equilibria in a game, have implications for identification, in particular will lead to partial identification. And whenever there's partial identification, there's a red flag for the Bootstrap to be valid. Missing data is another case where there's partial identification. But leaving those cases aside, if you're just, say, dealing with like regression and most of panel data, most of the cases that we cover so far where you're running linear models or the like, the Bootstrap actually works. And so if you're using roots that are asymptotically pivotal, you have a hope that the Bootstrap may perform better than just using the quantile of a normal. And so that's that. Hopefully then it's clear that the main three pieces of the Bootstrap is another way of approximating the distributions of roots. This is an asymptotic approach that depends on taking n to infinity. It's not a finite sample thing. But given this refinement idea that we discussed over here, there are 4 more reasons to say that the Bootstrap may work better than other cases, but it may also fail. And there are known cases where it fails. Okay. Other than this, I'm done for today. We got to the end. Next class, we're going to discuss 2 final methods that fall into the class of resampling methods. One is going to be called subsampling, and the other one is going to be called randomization test, which includes the so-called permutation test as a particular case. And that's going to be the end of 480. All right. For now, we're done for today. I'm going to stay here to answer questions.